Okay, time for problem 2. Okay, so we have a ring of positive charge. It's on the xy plane, and we have a point on the z-axis where we want to see about determining the plane. Okay, using symmetry and test charge arguments, draw an E-vector on the diagram. Placement and direction have a precise answer, and you can actually estimate the magnitude. Okay. So, because you notice that, let's see, how would we write it on an exam? Come on, there we go. And, so, I think there's more than one way to do this, but, and then, okay. Right. Okay. A. Oh, something went wrong there. It didn't go all the way down. So, Q evenly distributed. I guess we say 1 little I because it's part. All horizontal components will cancel. Every piece, every part of the ring has a matching part and opposite part. Okay, matching part would have been fine. And let's see, what else can I say? So only the vertical component survives. Survives. And points up. Q is greater than 0. So the net is going to point like this. And the magnitude is E here can be approximated just simply by KQ over R squared along the z-axis. Because P is there it is. Say R to P is greater than the diameter of the ring. It's kind of far away, something like that. Okay, what is next? DQ. Now I think, yeah, we got another. So be keeping in mind that a DQ has to be some infinitesimal. So I'm going to pick some DQ like that. And on the large diagram on page 11, so we're doing what it says. So that's my DQ. And create an equation for DQ, which, okay. So I'm going to say that I'm going to call this x-axis and the y-axis. So I'm going to define alpha, and the positive direction is counterclockwise. And I'm going to say I have a line charge, and so it's the total Q divided by 2 pi A. And I see then that, oh, I forgot to write the A on here. That's the radius. And then I'm going to say that if I have, just as before, whatever, so alpha times, or d alpha. So we are, once again, I have a d alpha. So d alpha times A is going to be the length of DQ, and then we'll multiply that by lambda to get DQ. Okay. What's next? Draw a DE vector. You know, of course, this is when it's a good idea to have a ruler. And, also keeping in mind that I'm going to have to change the zoom. Okay. So the DE vector, let's try a different color. So the DE vector is going to be here. And, get rid of the ruler. And there it is. DE. And, cool. It's positive charge, points away. Creating an equation. Oh, I did that already. Write the D using the DQ you made. So, right, I have to define my R. And this is one of those things where I get very lucky again, because the distance between DQ and P is constant. And so we're really happy about that. And so there's R. And so if I don't know if they told us the dimensions. Probably not. Oh, we do. Okay. 20. Oh, radius. Ah, right. So I see it right here. So R, and so it's 20 centimeters is greater than 5 centimeters. So the radius. So that's why I can kind of approximate it by being up that high. Okay, so let's just call this, we'll call it B. So A equals 5.00 times 10 to the minus 2 meters. B equals let's see, it was 20 centimeter diameter or radius. No, it's just the z-coordinate, it's not a radius, sorry. B has got a magnitude of 20 times 10 to the minus 2 meter. And well, we can keep R as it is, but eventually we'll have to calculate it. And it's constant, I meant to say that. So, what's next? Yeah, explain, so we have to write out an equation for it. So, dE is equal to K dQ over R squared. So that means that it's going to be K times A lambda. Where is the mouse? A lambda d alpha divided by A squared plus B squared. Okay. And, you know, the direction is in the r hat direction. Where is the... And actually r hat is drawn down below here, but I don't think I even bother with it because we have a diagram, so we don't need to worry about r hat. So F, so this is E, this is D, and then F is the variable, so we can use alpha since R is a constant, and dq is a function of d alpha, or however you want to write it. And then what's next? G. Yeah, we need a new angle. So DEX and DEY. I guess since I can clutter up my angle less, my drawing, I'll define beta. So well, now we have this one here is beta is actually going to be a constant, if you notice. And let's see, alpha will go from 0 to 2 pi. And so we have to express the x and y components as a function of x and y. So let's have a crack at it, huh? dEx is going to be r sine of beta, because it's the opposite. And so when x component is alpha equals 0 is going to be the maximum x component, so it's cosine of alpha. So when alpha equals 90, then there's no x component, it's only y component. And then when alpha equals 180, it becomes negative. It starts from 0 and gets more and more negative. So you kind of see now how the x components all cancel out. And dE of y, so in terms of beta, that's, angle beta, that's our cosine of beta. It's because let's be real careful here. Yeah, right. It's the adjacent of that, because beta, if I could find the cursor, beta is also up here. So, oh yeah, of course I forgot something. dE and dE, that's why I got confused, right? So now I can see it. The y component of this dE vector is cosine of beta. And then, of course, this is sine of alpha, because the y component will be a max at alpha equals 90. So, let's see. We look at our dE over there on the left. Total. And we see we have Ka lambda a squared plus b squared. They're all constants. And of course, now we notice something here. Give me a minute. Yeah, so this is going to be a squared plus b squared to the half power. That's this r. And so well, r equals a squared plus b squared to the half power. And then cosine of beta is constant, and then sine alpha d alpha. So this is now the dEy, and the dE of x becomes the same, oh, not quite. This part's the same. And that's sine of beta. And then it's cos of alpha d alpha. And, right. Yeah, then that's part H. So we had, this is part G. This is part H. See you in something else. And let's see, what are the two limits? Right, so we have to integrate the whole ring. So it's 0 to 360, or it's 0 to 2 pi. We need the whole ring. And what's J? And then do those integrals. Okay. So right off the bat, D E. Wait a minute. So that means E of X is going to be proportional to negative cosine is wait a minute. The derivative of sine is cos. So if we integrate, so that's sine of alpha, and so from 0 to 2 pi, then the sine is 0. So that's trivial. It just all the x components cancel each other out. Oh, goodness gracious, I made a mistake here. It's not that terrible. This is just a z component, and I gotta pause this. Two mistakes. This is the where is it? Where's Mr. Cursor? Okay. This is actually the horizontal component in the xy plane. Let's think about this. Well, that's why it's broken up into parts. I'm moving too fast here, but yeah, this test was kind of a bust because it took too long. Right, this is 3 dimensions. Duh. Okay, I wasn't wrong. Alright, so this is certainly the y component. And so the two of them make up the horizontal. And at the end of the day, they cancel each other because of the symmetry arguments. So what I did wrong here, though, is that this is also sine of beta. Because that's the component that's in the plane here, parallel. There we go. Nice. Yeah, great. That's it. I mean, there's like x squared plus y squared considerations, but this is fine. And right, if you integrate any of those trig functions from 0 to 2 pi, they always end up being 0. Okay. And equals 0 because the sine of 2 pi is 1. I mean 0, and sine of 0 is 0. And then e of y is proportional to cosine of alpha. Let's be careful. we integrate sine of alpha, then that's got to be negative cos, because the when you take the derivative of cos, you get negative sine. Okay. So, of course, once again, this equals 0. And so now we're left with the z component, which is going to be that's going to be proportional to cosine beta, and yeah, cosine beta just times d alpha. Yeah, that's it. And then let's make the dE, right, equals to dz equals dE cosine of beta, so that encapsulates that, and it doesn't depend on alpha, so there's no functional form of alpha in there. And then so that becomes E of z equals to the k times I gotta remember how to do that. Oh, simple. It was r over r squared, so then that means you're left with an r down here. And then and then cosine of beta is a constant, integral from 0 to 2 pi. Oh, and I forgot the a lambda. And of d alpha. Yeah. So then you see what happens is that the vertical component is actually somewhat smaller. Oh, give me a minute. No, you're gonna. Oh yeah, it's somewhat smaller because of the cosine term than if it was simply. So that when we estimated it, we said it was be kq over r squared, right? So here we end up with it to the half power here to be right. So that's I'll be careful. Pause. And let's see. So right, because it's r just as before, r cosine of beta instead of r sine of beta. Oh, no, I can't. There it goes. Yeah. So you end up with this expression. Yeah, something's bothering me. I still think simply having cosine of beta. So anyways, this becomes just alpha. So it's then 2 pi times k cosine of beta a times q over 2 pi a and divided by r, which I think is wrong. I think it should be r squared. And then the cosine beta is what makes it smaller than it would have been otherwise. But for the purpose of an exam, I'd let that be. And yeah, maybe the r's don't even belong here. Yeah, right, of course, because when I first started writing this, I was looking down here. It's up here. Yep, so that doesn't belong there. So that doesn't belong there. And yeah, we're all cool. Great. I like it. And yep. And then this doesn't belong here. So over r squared. Right, so there we go. Coolio. Okay. Oh, is there any more? Determine the magnitude and direction. Right. Ah. Oh yeah, of course, there's only a z component left, so the only difference is that instead of it, we added this cosine of beta term. That's it. And right, the 2 pi's cancel out. And there we go. And yeah, we didn't have to plug anything in. Neat. So the last section, I forget the letter. So J and K. Oh, J, yeah. Here's J. And then K is that the first thing we got was KQ over R squared, and now we have KQ over R squared times cosine of beta. And beta is going to be a small angle, so it's going to be, in this case, it looks like it's less than 30 degrees. So it's going to be very close to cosine of 30 degrees is 0.8660. So let's say beta is less than 30 degrees. So that means that cos of beta is greater than 0.86. So they're almost the same. And so direction, there's only a z component only. So that's the end. Okay, so let's see. Let's stop that.